In this video, I'll be going over chapter 2.8, which is one-to-one functions and their inverses. So an inverse is a rule that acts on the output of the function and produces a corresponding input. So an inverse essentially undoes or reverses what the function originally did to get us back to our original domain. So not all functions have inverses, but those functions that do have inverses are called one-to-one functions. So one-to-one is a function with domain A is called one-to-one function if no two elements of A have the same image. So in notation, this means that if f of x of 1 does not equal fx of 2, this is whenever x1 does not equal x2. So this also corresponds to if f of x of 1 equals f of x2, then x1 and x2 have to be equal. Which is basically saying if your y values, if they're not equal, then your x values shouldn't be equal. If your y values are equal, then your x values should be equal. So we could do this through a horizontal line test to test if a function's one-to-one. So it's going to be one-to-one if and only if no horizontal line intersects its graph more than once. So here I have a little diagram showing a one-to-one function and then showing one that is not one-to-one. So here we can see the one-to-one function, each domain value is mapped to a y value. But we can see here that if my y values are equal, then they should be mapped to the same x value. So here, g is not one-to-one because we have for b 4. So f of x1 equals f of x2. But here, our x1 and x2 aren't equal. 3 and 2 aren't equal to each other. So in this example, we have f of x1 equals f of x2, which is 4. But our x1 does not equal x2, as 3 does not equal 2. So g is not one-to-one. And doing this graphically, we could have our horizontal line test. And so we draw the horizontal line and it intersects the graph twice. So it's not one-to-one because here we have two different x1, x2 values and they're giving us the same y value, which is not one-to-one. Okay, here we have an example. So is x cubed and x squared one-to-one? So x cubed, yeah, it's one-to-one. We do our horizontal line test and it passes. So if our x1 doesn't equal x2, then our x1 cubed does not equal x2 cubed. So basically, no two different numbers have the same cube. So x squared is not one-to-one. We could do our horizontal line test and see that. And we could also see that for g of x equals x squared, we have g of 1 equals 1 and g of negative 1 equals 1. So we have two different x values getting sent to the same y value, which is not one-to-one. But if we were to restrict x squared to where the x's could only be positive, then it would be one-to-one. But we want to show that f of x equals 3x plus 4 is one-to-one for this example. So we're going to suppose that we have two x values, x1 and x2, such that f of x1 equals f of x2. Then we would have 3x1 plus 4 equals 3x2 plus 4. We subtract 4 from each side, and then we divide 3 from each side, and then we get x1 equals x2. So f is one-to-one. So we started out saying that we had x1 and x2, but we didn't say that they were equal. But this here shows that they're equal, and we know our f of x1 equals our f of x2. So f is one-to-one. Or we could also draw a graph of 3x plus 4 as well. It would just be like something something like that if it was straight. And then if we're doing our horizontal line test, we can see that it passes. Okay, so inverse of a function. So let f of f be one-to-one function with domain A and range B. Then its inverse function, f of -1, has domain B and range A, defined by the inverse of f of y equals x, such that then f of x equals y for any y and b. So what this is saying essentially is that if we do the inverse of our range value, then we're going to get our original x value. And this is shown by our f of x equals y in our original function. So basically our domain of the inverse was the range of the original function, and the range of our inverse should be the domain of our original function. So for example, we have f of 1 equals 5, f of 3 equals 7, f of 8 equals -10, and we want to find the inverse, f inverse of 5, f inverse of 7, and f inverse of -10. So our f inverse of 5, that should be equal to 1, because we had f of 1 equals 5. So basically we're thinking, okay, what value of x sent my original function to 5? And that was 1. F inverse of 7, so what value got sent to 7? And that was 3. And then f inverse of 10, we're looking for the domain of f, and that's 8. So 8 got sent to 10. So our inverse function property. So let f be one-to-one function with domain A and range B. So the function f inverse satisfies the following cancellation properties. So if we were to plug in the original function into our inverse, we should get x back for every x in A. And then if we're going to plug the inverse into our original function, we should get x back. So that's a good way to check if two functions are inverses of each other, then we'll get x in return. So we'll go ahead and do that in this example. We're going to verify f of x equals 3x plus 2 and g of x equals x minus 2 over 3 are inverses of each other. So essentially we want to show that f of g of x and g of f of x are equal to x. So note that the domain and range of both f and g are the real numbers. So we'll go ahead and plug them in. So for f of g of x, we do our composition of functions. So we have 3 g of x plus 2. We substitute in our g of x, so we have 3 x minus 2 over 3 plus 2. We cancel terms, so if we're going to distribute our 3 to the top, we would get 3x minus 6 over 3 plus 2. But then we would want to do common denominator, so we would get 6 over 3. So we would have 3x minus 6 plus 6 over 3. These 6's cancel. We're left with 3x over 3, which gets us to x. And then doing g f of x, so we're plugging in f of x minus 2 over 3, which is 3x plus 2 minus 2 over 3. Our 2's cancel, and then we're left with 3x over 3, and so we have x. So they are inverses of each other, so put verified. Okay, now we want to find how to find an inverse of a one-to-one function. So we could write our function as y equals f of x. So I'm just going to replace the f of x basically with y is what it's saying. It's easier to understand. And then I'm going to solve the equation for x in terms of y. So basically we want to get x equals something over here. And then we're going to interchange the x and y, so flip them. And then our result is y equals the inverse of f. So we're going to do an example. We want to find the inverse f of x equals 7x minus 5. So my first step is replacing the f of x with y. My second step is going to be getting x by itself. So when I flip them, I'm going to get, then I'll do the y. Okay, so I have y equals 7x minus 5. I'm going to add the 5 over. So I have y equals 7x minus 5. I'm going to subtract my y to the other side, and then subtract my 7x. So I had y equals 7x minus 5, subtracted 7x plus y equals minus 5. I've subtracted my y over here, and then I got negative 7x equals negative y minus 5, which is this part. And then I have, then I divided by negative 7. And then I could factor out the negatives from all these terms. So basically, I would have negative 1 y plus 5 over negative 7. So these negatives cancel. So I get x equals y plus 5 over 7. And then my last step is to interchange the x and y. So I just flip these. I interchange them. So I have y equals x plus 5 over 7. So the inverse f of x is x plus 5 over 7. Okay, here's another example. I want to find the inverse of f of x equals 5 over x plus 4. So I write y equals 5 over x plus 4. And then now I want to solve for x. So I'm actually going to multiply each side by x. This way I could cancel out the x in the bottom. So I have xy equals 5 plus 4x. And I want to get x by itself. So I'm going to move the 4x to the left. So I have xy minus 4x equals 5. That way I could factor out my x. So I have x factored out. Y minus 4 equals 5. I divide 5 by y minus 4. And then now I have my x by itself. So I can interchange the x and y. So I have y equals 5 over x minus 4. Therefore, my inverse of f of x is 5 over x minus 4. Okay, now here's another example. I have fx equals 2x plus 3 over x minus 1. So this one's kind of similar to the one that we had previously. So I'm going to have y equals 2x plus 3 over x minus 1. I want to solve for my x, so I'm going to multiply both sides by x minus 1. So I have y times x minus 1 equals 2x plus 3. And then I'm going to distribute my y. So I have yx minus y equals 2x plus 3. I'm going to add the y to the right and then subtract the 2x to the left. So I have yx minus 2x equals y plus 3. And then now I'm going to factor my x out. So I have x, y minus 2 equals y plus 3. And then divide by y minus 2. So I have x equals y plus 3 over y minus 2. Now I can interchange my x's and y's. So I have y equals x plus 3 over x minus 2. Therefore, my inverse of f of x is x plus 3 over x plus 2. Okay, now we're just going to check out how to graph the inverses. So the graph of the inverse of f is obtained by reflecting the graph of the line. I'm going to use across the line here instead. Across the line y equals x. So if we're reflecting the graph of the line across y equals x, we're basically going to be flipping the coordinates. And so it's going to be equidistant here. So I have y equals x, and then here we have f x, and this could be f negative 1x. Okay, so here's an example. We're going to sketch f of x equals square root x minus 2. Sketch the inverse of f, and then find an equation for the inverse of f. So our f of x is y equals square root x minus 2. And then basically what it's saying for f of x is that we're subtracting 2 and then taking the square. But for the inverse, we're going to square and then add 2. So whatever point here, we're going to be flipping them and having, so our x, these are our x, y's. And then here we're going to have y x's. So for example, this point here is 2, 0. And then this point here is 0, 2. So now we're going to find the equation for the inverse of negative 1. So we have y equals square root x minus 2, with our y has to be greater than or equal to 0. So we're going to get x by itself. So we have x minus 2 equals y squared. So we could cancel these. And then x equals y squared plus 2. Our y still has to be greater than or equal to 0, and it is here because it's squared. We interchange the x's and the y's to get y equals x squared plus 2. So now our x is greater than or equal to 0. So our inverse of f is x squared plus 2 with x greater than or equal to 0. Okay. Now we have this example. At a local pizza parlor, the daily special is $12 for a plain cheese pizza, plus $2 for each additional topping. So we want to find a function f that models the price of the pizza with n toppings. So we know that we want to model what it's going to look like if we have an n number of toppings. So our x should be our n value, and then $12 is the set price, so that doesn't change. So that's like our y-intercept. And then 2n is the factor because they charge $2 for each topping. So if you have 3 toppings, that's going to be $6 and so on. So that's our function. Alright, now we're going to find an inverse. And then what our inverse of f represents. So p, we're going to let p be price of pizza. So we want to solve for n. So we do p minus 12 equals 2n. And then we get n equals p minus 12 over 2. So therefore n actually equals the inverse of p. And so that is p minus 12 over 2. So our inverse function gives the number n of toppings for a pizza with price p. And so we could leave, we don't have to switch the n and the p back because this is the inverse of p and not the inverse of n. So if a pizza costs $22, how many toppings does it have? So we could solve for n doing the inverse of f, or the inverse of p of 22. And that's going to be 22 minus 12 over 2 equals 5. So it has 5 toppings. Alright, that's it for this section. I'll see you guys next time, and I'll be sending you guys information about the midterm coming up. So get prepared for that.